Hey folks, how's everybody doing today? Happy Wednesday. Wow, we have made it through July now. That's pretty cool. So we are getting there. We are definitely getting there. We're going to talk about dictionaries and hashing tonight. We'll see if we get into trees, binary search trees. We'll see how far we get. Hey, Professor Burp and Harishi, thanks so much for hanging out. I don't even know. Is that a little robot saying hi? That's cool. Yeah, I feel like they could use a couple more characters, but like to identify some of these channels, but that's okay. Ah. Very cool. Alright, so we're going to finish up dictionaries and hashing. We'll see how far we get into trees. And then next week we'll finish up anything left there. We already talked a little bit about heaps already. Oh, that's from yours. That's right. Okay. That's just Profess 226. Like, are you the 226th person whose name starts with Prof? It's funny like that. Like, why it could be more characters, couldn't it? It could just be your full channel name or whatever. I guess it was easier to type. That's true. Yeah, they're not going to do that for everybody. So, all right. And then any questions you folks have about the final project, I'd be happy to talk about. Again, the goal of this is you've got something at the end that you're proud of, that you can show off. A lot of times as you start interviewing for positions, yeah, all the coursework is good, obviously, but one of the things we typically look for when we interview people is, can they talk about a project that they did and like really give some details about what it was about, or what they found interesting about it, or what they might have learned from it, or some of the tools and techniques, all sorts of interesting stuff. Not just, hey, I did a traveling salesman algorithm. That's really boring. Like, anybody who takes a algorithms analysis course, we're not going to get that far in graphs. I mean, we can build our own, but it won't be great or anything when we start talking about graphs. But Like, what did we actually do with the project that was interesting is the helpful part. Yeah, I finally got an insulin pump, and this thing is beeping at me now. Like, it's supposed to be doing what it's supposed to do. It's confusing. I'm still learning it. But now I'm, like, officially part robotic, right? Because I've got an artificial pancreas hooked up to me now, plugged in. What was that, bionic, right? I'm a bionic man. All right. Cool. So any questions about the final project before we get moving? Excuse me. No? All right. Awesome. Let's see. Do we even have... Oh, yeah. It's kind of a quiet night. That's okay. Yes. Yeah. We're going to talk about the rubric for sure, Ray. Yep. You want to do that first? We can do that first. All right. So, again, we've got some of the basic stuff for the hand logic. We don't have the playable game itself necessarily. I've got something in there that's sort of like a playable game, but it's not exactly the same. But that's okay, and we're not doing the odds every time, that sort of thing. But we're going to use this odds of winning, drawing, and losing at each betting round. And we'll use this Monte Carlo simulation to keep it at about 10,000 possibilities or less. This idea that a random sampling across the distribution, right, respecting the distribution. And when it comes to poker cards, the easy part is just random, right? There's no, you typically get this card more often than this card because it's just completely random. So we just want to do a random sampling of possibilities. Okay? All right, so let's pull up a rubric here. You know what? I think I can. So I want to have both pages open. You can do it this way. All right, I'm going to build it here. There we go. This is for the final project. Again, there's no like in between. Either you get the points or you don't. I guess there's like partial, but that's, I don't need separate levels for that. So if it's missing, it's no points. Otherwise, it's complete. Complete. And we'll go with 5 for now, but I'm actually going to do this as a custom points here. So each one of these can be different numbers of points. We don't need this overall score. Okay, so 5 points just for getting the 1v1 Hold'em game is playable. Right? Get it to be playable so we can play around. Here, 5 points. Again, most of it's already here for you. Again, from what we had done in the 2151 course. That one's, most of the way there. And this is 1v1 instead of versus a computer, so it's going to be a little different with the computer that we had here in 2151, where we just randomly did something. Okay. So you alternate the automatic bet. We'll say $1 and $2. So there's this idea when you play, 2 people are automatically betting. They're blind bets before you even play. Like, just because you're sitting at the table, you're automatically in on every so many hands. And with 2 people, it's every hand you're automatically betting. Okay, and then we'll just ask the people to do that. Game is playable, right? Each round happens with the chance for betting. And then alternate the automatic bet before the first cards are dealt. All right, so 5 points just for getting that up and running as 1v1. Again, just kind of adapt what's there if you want, or completely scrap it, go with your own. Perfectly fine. Okay. Then let's see, because we want to display the odds of winning and losing at each round. So we want display winning, losing, drawing after all cards are played. So 5 points for that. So once all the cards are out, the 5 shared cards plus your 2 cards, right? We should be able to calculate the odds of winning. None of this needs to be through the Monte Carlo simulator, right? There are only 990 possible hands your opponent could have. Calculate the best possible hand for each of those possible 2-card hands. Right, so this idea, once you have all the cards out, there's only 45 cards left that you don't know. Your opponent has 2 of them. So out of those 45 remaining cards, right, when we did that, if I C2, nope, I want Wolfram Alpha. That's right. Bing search does not understand that. Wolfram Alpha. So 45 in combination 2 at a time. 2 at a time. 2. It's going to give me 990 possible hands they could have. Okay? So for each one of those 990 hands, then we have to find the best possible poker hand. Right? And a lot of that's already here. Right? So if you look at Hold'em hand, it has a get best possible hand that'll go through and find all 21 possible hands, make an array of hands, and find the best one. So that part's done for you, right? But you need to be able to use that and show the odds then when all that at the last round. Okay, so this is your chance of winning, this is your chance of losing, this is your chance of drawing. What we don't have is how to find these 990 possible hands. Right? So I'm going to have 45 cards because I know what 7 of them are. So I need to find the remaining 45 and make all the possible combinations out. So similar to what's done here, where it starts with the first card, and then the second card is the first +1 for the index. It goes and grabs those cards out of the index. Builds in this case, a 5-card hand. You're going to build a 2-card hand using the first card, and then the second card will start at +1 and keep on going. Right? So it'll give you all the possibilities. Right, so if you had, excuse me. So if you had your array list of 45, right? So index 44 is this last one here. Right? The first card will start here, and then the second card will go here, and then here, and then here, and then here, and here, and here, and here. Once we got down to the end, then the first card moves to here. And then the next combination, the second card starts here, and then here, and then here. And so there's 44 plus 43 plus 42 plus 41, right? On and on and on and on. If you think back to your math class, right? Ways that we can do this, because the first card moves, and every time the first card moves, there's one less second card available. Okay, so that one's not too terrible for picking out those remaining ones there. Then we're going to do this, so that's after the river. Right, once we have all the cards done there. Okay, and then we're going to say, so after 4 community cards have been played, we generate the 46 remaining 5 community card combinations. Because if you know what 4 cards are of the community cards, and you know what 2 of yours are, you have 6 cards that you know out of 52. That leaves the 46 remaining. So out of those 46, just you pick one at a time, right, to complete that 5 community card combination. Right, so you get 46 possible community card combinations. The 46 possible community card combinations, and then use those combinations. There's a B in there, right? Combinations to calculate or to generate the 990 possible opponent hands and find the odds of winning. Right. So for each of those 46, there's 990 possible hands our opponent could have. So 46 times 990, we should have about 45,000 possibilities there. Again, that's going to be a little bit high, and if that's a little bit more than 10,000. So if that's running slow for you, we'll try and limit that down a little bit. Okay. Winning out of the possible hands. So if this runs slow, you can use the Monte Carlo. Oh goodness, that's too long. Oh no. Okay, that's long enough. Is there like a longer description? I think there's a longer description. No, maybe not. Okay. So if that's going to be too long for you, then right, this was about 4 times as many. Maybe we take a quarter of these 46 possible ones and see what happens. This 990 is kind of important here, right? So we'll see. So yeah. All right, so 5 points for that. You know what? I think we might need to crank these up a little bit more. Let's see. Because if I'm doing 5 points each here, yeah, so I think these other ones we weighted a little bit heavier here then. So with the flop, let's do 10 and 10. No, are we still missing it there then? Oh, we need a couple more points here then. What do you think? Let's do 10 for this one. All right, so 5 for getting it playable, 1v1, kind of adapting that. 5 more for doing the odds, where we just calculate everything straight off at the end, right after all the cards are played. So that's after the river. Then 4 community cards, and we'll do the same. After 3 community cards have been played. There are 1,000 possible 5-card combinations, right? Because we know what 3 are, so we need to add out of the 47, we need to add 2 more. So 47C2, right? Is that 47C2? Give us that number. Yep, 1,081. 1,081 plus community card combinations. We only want to use some of those. So let's use maybe, say, 10% of those to generate the 908 possible opponent hands. So 10% of those would be like, what, 10, 11 or so? Yeah, that should keep us under the 10,000. The odds of winning. Okay. And then out of these, so before any cards are played then, so before any community cards have been played, we want to generate, so we don't want to do all of these, because this one is the big one here. You just want to do 1% of the 2 million possible. That's still like 2,000. That's still a little bit large. Maybe let's go with like 0.5% or so. And again, you can tweak these numbers. It doesn't need to be exact. You want it to be able to run on your computer. And if it's taking too long, then crank it down a little bit. Do less, do less, do less. So with this one here, it's not going to be too bad to generate 1,000 of them and then just pick 10% of them. You don't want to generate all 2 million and then go through it and pick 0.5% of them. So you want to just randomly generate the 0.5% number worth of these hands, of the community cards. Right? Use, and then we'll use those to generate the 990 possible hands, find our odds of winning. That makes sense? So that we're just kind of grabbing the things out of here that we're supposed to be doing. Again, adapting the game to 1v1. Sure, I've got, here's how you play against a silly computer that just half the time bets and folds. So just give the option. We'll just do the thing. and then you get 10 points for each of the, or 5 points for calculating these odds here, because it's almost done for you, and then 10 points for each of these. So you can tackle them kind of one at a time, or see if you want to try and share a little bit of logic between them. Either way you want to tackle it, that's perfectly fine. Does that part make sense? All right, so I got that rubric there, so we can attach the rubric. Use an existing rubric, final project. There we go. And then when we present, I'm going to ask you about how we're storing this data and why we're picking certain data structures. So if you're in a trio, you're going to use the odds of winning to have a computer player bet. So instead of it just being one player versus one human player, we can play against a computer player where the computer will bet, call, or fold if their odds of winning are 50% or more. Oh yeah, so this, that's right. So this, did I say a computer player before? I imagine this would be player versus player, not a computer. I think I had this in here wrong. I'm sorry. So add a computer or player versus computer option. Okay, so 1v1, one human versus one human. Okay, remember the odds of winning are different for each player because they each know what their two cards are individually. And obviously this is going to be a little silly, human versus human, because you're just going to see it on the screen. You'll see what their cards are, but that's fine. I wouldn't worry about that at all. The more interesting part is doing some of this analysis and then seeing how fast we can do these sort of things. That make sense? Oh, it's getting warm up here. All right, awesome. So let me fire up NetBeans here. Now we can start talking about the next stuff. Hydration, yeah, thank you so much, Professor Perp. Double, you got it. Almost done with my quad macchiato. There we go. Dusty, you too? All right, you got it. Let me make sure I got all that out. All right, time to change up beverages. I already have the ice in my nice tumbler, so that's what we're going with. This is not beer. Not today. Dictionaries and hashing, we'll see how far we get. Because we did want to, at some point, get through, close out some of these. Next week, right, that would leave, we basically did heaps already. It would just be trees, binary search trees, and graphs. I think might be doable for next week. Nope. Alrighty. Let me close these out. And I wish we had done JavaFX, because this is so much more interesting as a graphical user interface application rather than a command line interface. If you want to do it in JavaFX, have at it. That would be so much prettier, but you know, it's probably a little bit more, well, yeah, it's probably a little bit more work that way. 2353, so this is dictionary and hashing. So dictionaries and hashing are one of my favorite data structures because they perform ridiculously well at the trade-off of using more space. Remember, when we do our analysis, we look at time complexity and space complexity. So far, our space complexity has not been so bad. Right? We have generally oversized arrays to store additional space. At double, once we've doubled, that's at most the extra storage space we're taking. So at most, it's like 2 times the number of memory references we're going to need inside this array for storage. It's not terrible, not too terrible. Now, the linked lists, because every node in a linked list is storing other memory addresses, it actually uses additional memory. It's worse in space complexity than a linked list, or than an array list, because especially with our doubly linked lists that have the next and the previous links. Oh man, my eyes hurt today. If we have, let's open up the whiteboard again, I guess. There it is. I'm going to clear this one out. So in an array, right, each one of these is a memory address. Right, so 64 bits, 64 bits, 64 bits for the memory addresses, on and on and on and on. Right? For everything that I'm storing, this is where that object is. This is where that object is. This is where that object is. So the objects themselves don't need to be contiguous, but my array of references to them is contiguous. With a linked list, right, remember, I'm going to say, hey, this is where my object is, 64 bits, and then my next and my previous, those are memory addresses, where that other node is in memory, right? This itself is a node. Here has a memory address. So this one stores where the next node's address is. So for every one of these, we're storing 3x the number of memory addresses. Right? And then the next node will store its previous, its next, and its actual 64-bit thing. So each one of these is 64 bits still. Because it has to store, well, where's that next thing? Where's the previous thing? So linked lists aren't great in terms of space analysis. They're not awful, right? It's still linear, again, but we understand it's slightly worse linear because it's 3 times the memory addresses versus just one memory address, possibly doubled. So at worst, we're at 2x here. Like all the time, we're at 3x with the linked list. Oh, excuse me. All right. So far, all of these objects here, right? These have all been lists, right? List of objects of whatever type we want to store. With a dictionary, we're changing up the type. The idea with a dictionary is that you have a key and an associated value. So, like a actual dictionary, you have a word is your key, the associated value is the definition. So you find any word you want, you say, hey dictionary, give me the definition of this word, give me the value associated with the key of this word. Right, so we have word associated to definition. For an actual dictionary. The dictionary data type is the same idea. We have a key that will uniquely identify something. So the key here, these are unique. They have to be unique. Right? You can't have the same word in there twice. Now, I know dictionaries have the word in there essentially more than once, but it's the same word with multiple definitions. So the value associated is just three different definitions. So it's still one word. It might have a single definition, it might have multiple definitions, whatever it is. It's still a single word instance there, right? So the key needs to be unique, and then you have an associated value. Now, what we want here is to be able to look up these keys very quickly. That's the important thing. So far with all of our... Why is that beeping at me again? Friend. What is going on here? Huh. Sorry, it's saying my sugar is still really high, despite a bunch of insulin is supposed to have pumped into me. Don't know. We'll just give it a little more time. That's a weird thing. I'm still new to this. All right. So far when we looked at searching, right, the best we could do is if we were sorted, right, we could do the binary search, which gave me big O of log of n, this logarithmic of n, right, where I'm cutting half each time. Here's the next half, here's the next half, 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 half. So that's pretty good, but it requires things be sorted, right? So inserting into a sorted list was slow. Remember, either we were an array list or a linked list. Either one is slow. Array lists are slow because we have to add and then everything else has to bump. Linked lists are slow because we have to find those links. We can't actually do a binary search in a linked list because we don't have indexes. We can't immediately jump to the middle and then jump to a quarter and jump to an eighth or whatever we're doing here. So because we're being sorted, it makes life harder for us. Right? We like being able to find things in O of n or log of n. That's nice and fast. That's a good way to find it here, logarithmic of n. But inserts are slow, right? Inserts are always still going to be O of n, because we either have to walk so many links to find it in a linked list, maybe half, maybe it's near the end, maybe it's near the front. We don't really know. Or an array list, we have to bump n things down if we insert them. So that's really slow. So a dictionary actually solves this problem for us in that we can do inserts in constant time. And we can do lookups in constant time star. Big fat star there. Again, we're talking about averages here. Averages. And hopefully you're thinking to yourself, wow, that's really good. Right? If we can insert, if we can look up, right, all create, read, update, delete, do these operations all in constant time, that is pretty fantastic with a dictionary. That's what we want to do. Right? And implementing it with a sorted structure would not be good. Implementing it with an unsorted structure is still going to be slow to find a key. Right? Find these here. We'll take a look at this one first. All right, so starting in chapter 19, we'll kind of work our way through some of these ideas here, and then we'll get to how we can get to these good performance. It is really cool. And dictionaries are fantastic because we can store basic keys, right, and then interesting objects if you want. So maybe we might say, I'll have a collection of students, and I want to be able to look them up by their ID, student ID, because that's a unique identifier for you. Right? So my key might be the student ID, and the associated value might be an object, a student object. Got lots of ways we can do that. So other terms you might have heard for dictionary might be map. Right? It's a map. Here's the key and the value. We're mapping a key to a value. Right? Either way is fine. Or like a associative array might be another term for it. Like two arrays that are like kind of side by side. You could do similarly. That's not a great way to do it, but you can. So things that we can do, right? We can add, we can remove, we can get the value associated with it. We can ask if it contains a given key or not, whether or not it's empty, those sort of things. So looking at the actual dictionary interface, we could write one for ourselves if we want. We're not going to bother with that right now. Again, I appreciate how the book goes through and does that, but I feel like it just adds more work for us because we're not going to go through all of the exact examples again here. All right, so that's sure. So store some phone numbers. Frequency of words is fun. That's a fun one. Concordance, yeah. All right, okay, that was a boring chapter. 19 was short. It was just like the idea of dictionaries. So then in chapter 20, looking at some implementations is much more interesting. Looking at, well, how can we do these sorts of things? And again, we're not going to get to this one-to-one at one constant insert, constant lookups, star, until we talk about hashing next. But we'll look at some basic implementations, and we'll talk about hashing. So hashing is the key to making this work. Spoiler alert. So we could have an array-based implementation, right, with associated keys and values. We could do that sort of thing. But the problem is all of our performance is O of n, essentially. We could have a sorted array, again. So finds are going to be really quick with a sorted array, log n, but adding and removing, even trying to find, just walking through it, it's O of n, takes n operations because of the having to shift everything down. Once I insert, it has to bump. Right? That part makes sense, right? I feel like we've talked about that already when we did our arrays and linked lists. We could have sorted links and unsorted links. They can still perform the same way. Those aren't great implementations. So I don't want to spend a lot of time looking at the bad implementations. I'm hoping the problems with those bad implementations were obvious. And tell me if they're not. I don't want to take that for granted. I'm sorry. All right, it's loading here. So the idea with hashing is that I can take an object. Should probably write a little near here, sorry. An object, and I can get a hash key from it. There's a couple rules about the hash key that are important here, right? Is that the hash key needs to be constant. So it means it cannot change once you have an object. So every time you have an instance of an object, the hash key needs to be the same for that instance. Okay? Oh my goodness, where did it go? Why are those the different things here? That's not helpful. So, gonna ban that word. Okay, that's a 5-minute ban, right? I think that was the deal for those points. Let me see. Yeah, 5 minutes timer. Okay, so till 6:45, I can't say that O word there. So the idea here is that this is just a constant int value here. So for primitive types, like integers and floats and doubles and things, it's pretty easy to generate a constant hash key. Right, so every time you have the value 27, its hash key will probably be like 27. Right, it's for itself. Strings aren't so bad either, because strings are immutable. So a string can say, hey, for each character, right, get the hash key, and probably add them all together. Right? So you can actually go and get the hash values of a bunch of objects here. So let's have an int numbers 42, we'll have a string value is testing, I don't know, sure. And then let's print out these number dot, oh, sorry, that needs to be an integer. An integer number dot hashcode. So hashcode is a method that is inherited from, you guessed it, that word I can't say, that all classes inherit from implicitly, right? It comes from, if you don't define one, you get one from that class. You can implement one in your own class if you want. Right, so then we can say the hash code for testing is plus the hash code, and hash code for 42 is, right? And every time we run this, we should get the same hash code. Give it a shot. Oh, friends, my plugins are not working. Filing. That NB Java C plugin. I think the plugin is just screwed up, and I haven't bothered to fix it yet. All right, so 42. Sure, that's the hash code for 42. Great. This negative, what is that? 1.4 billion. Let's see if that stays. Should stay. Should. Yeah, negative 1.4 billion. Awesome. Awesome, awesome, awesome. So the hash code is constant. That's important because what we're going to do is we're going to use the hash code to look up a value in a dictionary. So if we can get a constant, unique value for an object, we can use this hash code to do some cool stuff for us here. So what we're going to do is we're going to make a array list. And now this array list, it's really of type integer, because that's the key that we're going to use here. No, I'm sorry. This let's just make it a type object. This is my data. There's a new array list. And then what I want to do is I want to just add a bunch of empty values here. So let's say for int value 0, value less than 10, value plus plus. Actually, let's do 11. 11 is going to work out a little cleaner for us here. Now let's add null. I'm just going to add nothing to data here. Oops, can't use value. Okay. Index. Let's add a bunch of empty indexes here. You know, we can just make this a basic array. I'm sorry, let's just make it an object array. Data, new object array, size 11. We'll just make it nice and easy. That way I don't have to go and add a bunch of values here. Now, defaults are going to be nulls. Right, so for object, I don't know, object in data, we can print out the object. So it should be a bunch of empties, a bunch of nulls. Right, and maybe we want to print out the index as well. Oh, shoot, so we should do an index loop. So for index is 0, index is less than data.length, index plus plus, and then we can print out index plus index. Let's use a string format. String.format. Index, a digit there, and I don't know, just a dash maybe, and then a string. So the index and the data at index as my object. Oops, start at 0. Why did I start at 1? I missed a semicolon. My goodness, I cannot type, folks. Right, so at all the indexes, we have a bunch of nulls. Great, not a problem. Then what we're going to do is we're going to say, hey, let's add something. Well, so where do I want to add these values here? And again, this is sort of silly to do with type object, but don't worry about that. We'll do a cleaner version in a little while here. So what we want to do is I want to take the hash code of my object that I'm adding. So let's we can do a method for it, right? Public static void add item to a object array data and an object item. So we're not doing the key value pairs currently. We're not doing a full map. We're just looking at what I can do if I have these hash codes. So I can take the data. All right, I need the length is my data.length, and then the hash code of the item. This is what length of data storage. The hash code of the item is going to be my item.hashcode. And because it's been more than 5 minutes, right? So because everything is an object, right? Implicitly, everything is an object. I can always get a hash code out, right? And it should just work. It should give me the correct one here. So I'm going to get the hash code, and then I'm going to get an index position is going to equal the hash code modulus the length. Remember, this will divide out the length and give me the whole number remainder. So I'll get, when I'm done by dividing by the length, a number between 0 and 10. That'll be the index position to put item. And I'll take my data at the index position to put the item, and I'll assign it the item. Okay, so then we can add an item. How about we do this? Let's refactor, extract, or introduce a method. Here, we'll make this private, sure. So this is what, print data. There we go. So we can print the data. So I'm going to call add item. We're going to give it data, and we're going to, how about we give it the number? And then we'll print the data. And then we'll add an item. We'll add that value. Set the value, and then we'll print the data. Let's see what we get here. Oh, goodness. Index out of bounds exception. Oh, negative. Okay, so negative is no good. So let's see. So if hash code of item is less than 0, hash code of item times equals -1. Right? Let's make it positive. Right? If it's negative, make it positive. Easy. There we go. So now it's empty. Right? We get all the indexes. Now we're going to add 42. It got added at index 9. So 42 mod 11, modulus 11 should give me a 9. It gets put here. And then when I add testing, whatever that value was, mod 11 gave me 6. So I'm able to add items based on their hash code. Right? So the other thing I can do then, I can have a method, public static object get item, given the object array data and an object item. Again, this is sort of silly because this would be better for a key value pair, or what, I don't know, contains item. How about that? Contains item, and we'll return a Boolean. Okay, let's see if we contain the item. So we want to check the same thing here, right? Right, the same arithmetic. So if I'm doing that exact same thing, sure, let's extract it as a method. Refactor, introduce a method, get index for object in data. Okay, so we can get the index for the object in the data. And then we can say, hey, if the data at the index position, put the item, is dot equals the item, return true. Otherwise, we're going to return false. Well, I guess really we could just return this then, right? So return equals the item. It's either true or false already. So you can see, hey, do we contain that value? We can print contains the data and how about the value? Do we have that string? It should be true. We should have it. Okay, how about do we check, do we have, instead of the value, how about testing? Can I just give it a string, get that back out? Nope, does not contain quote testing. Oh, goodness. Oh, that's a lowercase t testing. Uh-oh. Yep, they hash differently. All right, true. That's what okay, that's what I was hoping for. Goodness. And how about if we contain, how about 42? Do we have that one? Yeah, we have a 42. Looking good so far. How about do we contain 7? Oh, goodness, we have a null pointer exception. Well, that's no good. So this equals here is actually backwards. Where is it here? Where'd it go? Dot equals. So it should say the item equals this one. Dot equals. Because I'm always going to have an item, I think. I might have a null at that location, though. So I can't say null dot equals, but I can say item dot equals a null, and it should be fine. There we go. Now we get back a false. Good. And again, if we gave it a different value here for strings, that was fine. It's weird it didn't actually... So testing must have came up to the same hash location. That's interesting. All right, but you sort of see this idea. If we can get a hash code for an object, we can quickly, in constant time, go find where it belongs in my dictionary. Right, look at that. We don't even need the array list. Does that part make sense so far? Now, the problem here is, what if I have values that get different hash codes, but when I modulus it, right, by my length, if I get the same index, that's going to be a problem. Because then I need a new place to put it, because I don't want to blow away what used to be there, because I should be able to store them. They're different. So we have a couple strategies here. That's called a collision. So if we get the same hash code for two different objects, or I'm sorry, not even the same hash code, but if we get the same index for two different objects, we have a collision. And we're going to have a problem looking them up in, this is called the hash table. Right? This array is the hash table. This table of the hash values here. We're going to have a problem. So we need a way to solve that. Now the book goes through a couple ways you can solve that. They're not great. It's not ideal for sure. Yeah, probing, linear probing, quadratic probing, open addressing is not great here. I'm a fan of separate chaining, this idea of being a bucket. I think the chaining is the best approach for that. So we're going to look at separate chaining. That's going to be, I think, the easiest approach for us. And that we get into now, chapter 22. We're actually doing really good, folks. You folks are awesome. So we start up a new class here. And let's make this this is a, what, chained dictionary. And our chained dictionary will be of type key and value. So usually we've used key as a generic type. In this case, we have key and value. So the letter T itself doesn't actually have a special meaning. It just means, hey, it's a generic. You can use other letters here to represent those types. Okay? Yeah, 22 goes into a lot of cool stuff, but that's all good. So we're going to do a chained dictionary. So it's going to have a private array list, or just an array, right? So this will be our private array, and we want to be of a given type. Well, what we want is an entry. Essentially, we want to have, hey, this is the key and the associated value. Right? We want to be able to use a key with an associated value, and I want to be able to store those in that list. So for any key and for any value, I want to make pairs of them there. So I want to have another, essentially another class that I'm going to use for storing them. Where'd that go here? Let me make sure I've got the right. So iterators. Yeah, Java has it in the dictionary, the Java map, hash map, and hash set. Excuse me. We can use those built in, but these are a lot of fun to build ourselves. And then hopefully it makes a little bit more sense if we look at building dictionaries out ourselves, how they're going to perform for us. So we need, where is that here? Because we want the pair. That's fine. Oh, okay, yeah, he calls his a hashed dictionary. So we're going to have a table entry of key value array, which is our hash table. So we need a table entry class here that's going to represent what this is. So we have a private static class table entry of a, now we don't want to reuse the K and V here. It can be a little funny because we already have a K and V here. So it uses like S and T, a private S key and a private T value here. And then we'll add the constructor table entry S key T value. So this dot key equals the key, and this dot value equals the value. Oops, no, key. There we go. And public S get key, turn the key, and a public key value, turn the value. Okay, so we can get the key, and we can get the value. So we're going to have an array. Our hash table will be of table entries, which is a key value pair. So that's what we're going to store. Okay, so it's private and belongs to the chained dictionary because no one else needs to know that we're using these pairs here. We don't need any of that. We're also going to track the number of entries that we have here, and we'll have a int yeah, that's the number of entries. It should be fine. That should all work. All right, so we make a new dictionary, a new chained dictionary. We're going to take my hash table equals a new table entry, K and V, and we want to set our size. Now, there's some really cool math that goes into this. We're going to be lazy and do the bad math, right? So don't be lazy. This in real life, and thankfully it's not actually like that in real life here. Oh goodness. Generic array. What? We have to make a new object array and cast it. Is that what we have to do? Object array. Why is this always so obnoxious? Sorry. You don't want to use even values here. Prime numbers make much better values here because when you do the modulus, you're going to get a better distribution. Use prime numbers is best. But again, that's probably more complex than we really need to get into right now. Yeah, table entries of a new. Was it this table entry? Ah, no. Oh, come on. Still complaining. Table entry cannot be converted. I don't know why Java is so obnoxious. We cast it as the type table entry key value array as an untyped version. Sure, that's fine. That's fine. Okay. I don't think that's fine. All right, so that sets up the dictionary. Right. So again, we're going to size it at 10. That's okay. We can fix this part later. But now we want to do separate chaining. Oh goodness, that table entry is not. That's not going to do it for us either. I'm sorry. We need a bucket. Well, that's annoying. Where's my bucket? All right, we'll just do this instead. So let's make this here instead of a hash table of table entries. Let's make it an array list of type. There we go. Nope, where am I missing that? New array list. Does that let me do it? No, it doesn't let me do it. Key value. New array list. Array. Size 10. Nope, still doing like that. My goodness. Friends, I'm sorry. This is obnoxious. Is that gonna work for us? Table entry, maybe? It's the new array list. This idea that we want each entry to be a bucket that we can put things in, so that when we have the same hash values come out, or the hash indexes come out, we can just drop them into this bucket and start stacking them on top of each other. So that if I were to have, right, this essentially I'm putting a bucket at each index here. This is the chain. So each one of these then is going to have the next value. So maybe I'll drop something in, 4, 5, 6, 7, sure. So I might drop, an item in here, and then maybe I'll drop another item on top of it. We can have the first item or the second item or the third item. We have lots of items inside of here, right, if they all happen to land that direction. We could do that sort of thing. So the buckets make it nice. The previous chapter talked about this linear probing, where you say, well, if they have the same one and it's full, just put it in the next one. The problem with that is you're going to end up with gaps as you start removing things, and that's really bad. So if you don't do the chaining and you just do, hey, let's just put it in the next available spot, and you take the item back out, you might have a gap here, right? If we instead of stacking them here in a bucket, if I just put the next available one here, the next available one in the next available spot, then if I take this one out and this one's gone, and I go look for this one, I'm going to look here and say, nope, I already have something there, but it doesn't match. Look at the next one. Oh, it's empty. I must not have it. So doing that probing approach is really problematic, because then things need to shift and you run into all sorts of trouble. So this chaining approach or bucket approach is much nicer. We just drop items with the same hash code compressions, the same indexes, just into a bucket. And then at most we'll have a couple items there. It's not usually too bad here in terms of how many items are going to be there, because generally hash codes are distributed pretty nicely. Generally. And I guess it's sort of a hand-waving trick, but most objects can hash themselves nicely. Now, if we write a class that hashes itself, we can do it badly, and we'll run into trouble. That's what this big star is for this performance here, is if this is only if hash codes are uniformly distributed. Right? So if I can uniformly distribute hash codes across a wide variety of objects, instances of objects, then I can get O of 1. Otherwise, my bucket approach here is just, they're all going to stack up at 4. And if I have n items all at bucket 4 and nowhere else, obviously it's not going to be very fast, because I'll have to look at the first one, look at the next 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 one, until I find the match, or I didn't find it. That's essentially a linked list at that point. We kind of like this idea of a bucket here. Okay? All right, yeah, let's not do the array list. Forget that. We'll make a table entry array. Forget that. Just make it of type table entry. Table entry. Missing, where's my, there we go. So let's also then have a private table entry next. Table entry of S&T next. And we'll set next equal to, all right, let's do that one. We'll do another constructor then that takes a table entry ENS next. This next equals next. So we'll just do this with key, value, and null. So if you don't tell me what the next is, I'll assume it's null. Otherwise, I'll take it. Next, next. Oh, did I do it backwards? S&T. S&T. There we go. I did do it backwards. And so the table entry itself can be chained for us. We'll make the chain here. Right? We'll have that hash table of table entries. That should make life a little better for us. And then a public table entry type S&T, get next, return next. Okay. So the idea here then, what we're going to build out is an array, right? And each one of these then will have a key, a value, and a next for each location. So if there's a next one, we'll have a key, a value, and a next for each index. Right? If there's nothing there, great, nothing's there. If there is something there, then we can start comparing. Okay, let's go to add item. So public, what is our add? I think that's a void. Get value, remove, locate. Okay, so add is actually going to return a type V here. So add a key, the value. So if you give me a key and value to add, I'll give you the old value if it existed. Okay, to make sure that, because the idea with the dictionary is that you can only have unique entries. So if I add the word Eric, and I add a definition for Eric, and then you go and say, oh, here's a definition for Eric, it's going to overwrite the old one. So I'll give you one last chance to get that old value back out. So we're going to see where it belongs. We need to find, right, our hash index. So we need to get the hash index given the key. So we're going to get hash index equal to get hash index given the key. And we need a method for that. So let's make a method. So to get the hash index, we're going to return key.hashcode modulus my hash table.length. That'll be the hash index. Get the hash mod the length here. And actually, maybe we should have checked for that negative here. So, okay, so before we do that here, so int index is equal to, then if index is less than 0, index times equals -1, we can return the index. Okay, to do the checking, just like we ran into that over here, to get our index out. Get the length, the hash code, if it's less than 0, right, here's the index, that idea here. So I get the index to put the item. So we got an index. Now I want to see if something's there. So if my hash table at the index is equal to null, then great, no problem at all. Set it to a new, what do we call it here? Table entry, new table entry of key value type, given the key and the value. It has no next, right? Not a problem here. Okay, and we're going to return null. Nothing there. No previous entry. Oh, we can just use the diamond operator. Sure, that's fine. So if there's nothing there, great. If there is something there, right? Now we need to see, well, is it the equal to, is the key equal to the key you gave me? So we're going to check. So we're going to say, here's a table entry of a key and value type. This is the current entry is equal to hash table of the index. And we're going to loop. We're going to say while the current entry does not equal null, we can keep on going. Right? As long as we didn't get to the end. So it's because we're going to do this walking thing with the links. We're going to take this link, go to the next one. Take this link, go to the next one. Take this link, go to the next one. So as long as it's not null, we can keep on going. So we'll say if the current entry dot get key dot equals the key we were given. If the keys match, then we need to replace the value. So we need the value, or old value, right? Old value is equal to the current entry dot get value. Current entry dot get current entry. Oh, it's just value. Sorry, just that's weird. I changed the name of that. That should be get value. All the other ones are get value. We'll go back to get value. Get value. Okay, and then we're going to say, hey, the current entry. Oh, we need sets. I'm sorry. It needs set for value here. So we need a set value. Like void set value given a t value. This value equals the value. Okay, so then my current entry dot set value given the value. We'll go set it. And then I can return the old value. Method's done. If it doesn't equal that, right, then my current entry will equal current entry dot next, get next, right? Get the next value out. If that matches, great, replace the value, return it. If it doesn't match, go to the next one. If it doesn't match, go to the next one. If it doesn't match, go to the next one. If I've gone all the way to the end and I haven't found it yet, then it means it doesn't exist in here. I don't have a current one. I'm going to add it. So what I can do then is I'll say, hey, My hash table at index equals a new table entry of key value pair, given the key, the value, and what is next is what used to be first. I now have a next. Right, so this is saying, hey, you're now the first item in this singly linked list of items. Makes life easy. So I'm just going to put it at the front here. Right, it's the new front, and that's the first one checked next time. So I'm making the chain of items. Okay, and then if I do that, I'm going to return null. So either it was empty and I add it, or it existed and I overwrote it, or there were items in the bucket already, and I'm going to add a new item to that bucket. I like having key and value here. I'm going to leave it. Makes me happy, even if it upsets me, or upsets NetBeans. Does that part make sense? How we're going to say, okay, let's go add a value here then, with a given key and value. And, okay, sure, prime numbers. That's fine. Okay. Now, the problem we're going to get with number of entries needs to go up by 1, right? So if we added the new one, then number of entries plus plus. If we replaced, that doesn't change. If we added the new one, number of entries plus plus. Right? Because we didn't actually add an entry if it got replaced. So we only want to do that if we're adding new entries here. I like that. Okay. So the problem with these hash tables is that if I get too many key value pairs, key value next, key value next, right, if it gets too full and we have a lot of these chains, it's going to be slow. So there's this idea called a load factor. Load, that's an A there, factor. And people who are really good at math have studied this sort of thing and found out the ideal load factor is somewhere around 0.75%. 0.75%, that's a Nope. Those are different things. About 3/4 full. That's an F there. So about 3/4 full is your ideal load factor. Again, it can vary, right? So it is when I have a capacity of 10 indexes, I want no more than 7.5 items. So like once I have 8 items in there, 8 out of 10 is greater than 3/4, right? Yay, math. So we need to resize our dictionary. So we resize it a very similar way that we resize our arrays, right? We need to double our space, or essentially go to the doublest next prime. I know that sounds stupid, doublest next prime, that's awful, but you want to make sure you're at least doubling to make sure that we get that amortized average happening, right? If we do that doubling thing, when we amortize the average time it takes to do something, even if I have to double occasionally, my performance will still be constant. Because right now, no matter how many n items I have, assuming we get a good distribution, right? That's the big assuming we get a good distribution. When you go add something here, it's a constant time to get its hash index, and then it's essentially going to be constant to find does it belong in the bucket or not. Because we're assuming these things are distributed nicely across the bucket. So again, it's a little bit of assumption there. But if we get a good distribution of hash codes, and we're using like good prime numbers and things like that for indexes, it will hash and index appropriately, and we'll get good performance. So kind of hand waving there, but you know the whole idea of using dictionaries is based on the fact that we can get good distributions of hash codes. So if you're using one, it's assuming you know how to do a good hash code. And if we don't do good hash code, bad stuff happens, right? And we just kind of have to accept that risk. So this idea with the load factor is essentially we'll have to resize ourselves. Right? So we can check to see if we need to resize. Void check for resize. And we can say if my number of items, number of entries is greater than, what do we say, my hash table length times 0.75 or so. And again, this is sort of ugly here to have that as a value, so we probably want a private static final double load factor 0.75, like something nice and clean and pretty, rather than a magic number, right? So like, here's the load factor. We'll just define it once. That way I have the word load factor in here instead of a magic number. Okay, so if we are that, then I'm going to have to resize. So to resize, well, I need to double the size of my table entries, and then I need to go rehash everything out of the old one into the new one, which is no small pain. Right? That's not the easiest thing in the world to do. But what we're going to do is we're going to do this. We're going to take the table entry of key and value old hash table equals the hash table, and then the hash table, oh, not that one, equals a new one of these. Given the old hash table dot length times 2. Again, use primes, please. All right. Illegal start of expression. Array. There we go. Isn't that what I did? Didn't I copy and paste that line? Goodness. Nope, I did it wrong. Not 11. We want old hash table.length times 2. So again, use the primes. There's a great little like pseudocode find the next prime value. That's more complicated than we need right now. We'll just hand wave and say it's okay. So if we do need to resize, we'll make a brand new hash table. Then what we're going to go through is we're going to get every value out of the old hash table, and we're going to re-add it. Okay, so we're going to say for table entry key value entry in the old hash table, we're going to say a table entry of key and value current entry equals the entry, and while current entry does not equal null, we're going to go call add the current entry get key current entry dot get value. We're going to go re-add the key and value. Then we'll take current entry equals current entry dot get next. Then we'll go to the next entry. Add every key and value pair, so it's going to rehash everything in the newly sized hash table. So this is rehashing everything in there. So again, it's going to take n operations, but if we're only doing it every time we need to double in space, on average, right, our amortized average performance will still be constant. That's the hand waving. I don't know. Check for resize. Maybe that's what it's, sure. And we should do that probably at the end of every add, right? So if we're replacing, we don't care, but if we're adding something, we do care. Okay, we can check for resize when we go add an item. All right, we okay so far? Oh man, it's 7:30 already? Friends, you've got to stop me if we don't take a break. This is a little heavy, right? A little heavy. Super interesting stuff. Like dictionaries are one of the, I think, the best data structures out there, because we can get constant performance for find, constant performance for add, constant performance for remove, assuming we get uniform distribution of hash values, of hash codes, which is not the hardest thing in the world to do. It's not the easiest thing, but it's not the hardest thing in the world to do. Okay? What do we have here? What's my... What? Python dictionaries are fantastic. Yeah, Dusty. Python dictionaries are so nice. They're so easy to use, too. I love Python. Where is it upset with me? Line 39? I don't know why that's so upset. That's okay. We'll see if it builds, maybe. See if it'll build. All right, so why don't we take 10? I'll put some music back on, and we'll see what's going on here, okay? Yeah, build fine. So I think those action items are just that being slow. It'll take a couple minutes. Music's not too loud, is it? Oh, wait, hang on. I wanted to do this. I wanted to do play all. Okay. All right, cool. I got all of his music in here then. I had like 2 different albums, and I was only doing 1 album at a time. But we've done this one before. Let's skip. Now let's shuffle and repeat. Oh, shuffle was on. Sorry. All right, folks. I'll take 10. We'll be back in a little bit. Hey, folks. Oh, I forgot to turn the audio off. That's weird. Sorry. Wrong mic. Alright, how do I... My goodness. I'm so bad at this. There we go. Now we can fade it out. I swear I've used a computer before. Alright. Cool. So let's go back to our chained dictionary here. See how we're doing. Let's go see if we can use it. So again, I guess we'll leave some of these things here, but they're kind of ugly. So we'll maybe move all this out for, we'll just call that demo. Like static void demo. There we go. So then I'll just comment out demo, because we don't need that. So let's make an instance of our dictionary. So let's make a chained dictionary. Nope. Chained dictionary. Why is that not? Oh goodness. It got in the default package. That's not right. New factor. Okay, that was weird. I don't know what I did there. Chained dictionary of type. So our what should our key be? How do we do by integer? Integer. And we'll do, I don't know, a string for now. Again, probably want to use an object, but we can get to that later. We'll call this my students equal to new chain dictionary. Great. Now we have this. So now I should be able to add okay, so what integer do we want to add? So we'll add a student ID. How about 123 is your student ID? And your value is, that'll be Bob. And then we'll add 124. We'll add Jane. And we'll add another student at, I don't know, about 235. We'll add Mary. And 450, we'll add Quinn. And, okay, that's probably enough students for now. Make sure it actually adds without crashing. See what we can get. Uh-oh. Unchecked. Is that what it was here? Uses unchecked or unsafe operations. Oh, goodness. Unchecked or unsafe operations. Where was that happening? Probably when we did that table casting, right? Oh, geez. Okay, we gotta find that there then. There's a little note we can add there to make it ignore that. Okay, yeah, we want to press the warning. There we go. So we'll say at suppress warning unchecked. Is that not working for me? Why is that not? That should be fine now. So we can run it. Oops, run this one. Nope. Oh, friends. Where do I need that? Should just be able to add it. I'm sorry, folks. Let's see. Where do we need to add that? Press the warning. Yeah. Fine. We'll just undo. Pull it out. Isn't it upset? So we can build it. There it goes. I want the details. All right. Recompile. Properties, compiling, add an option, unchecked, excellent. That might do it for us. Let's try it. Let's build. No, that didn't do it. Does it run? Oh, ran that time. That's funny. All right. Is that all we had to do? That's really weird. It seems wrong. Oh, right here. There we go. Oh, there's the example. Move that one. No? All right. Sure. So just adding that made it happy again. I don't know. He got upset with us. So let's get our update out of the chain dictionary. So let's go get the value. Right? We want to get key. We'll have a public v value or public v get value given a k key. If you know what the key is, we should go get the value back out. So again, we do a very similar thing here. But we're not adding anything new. We're going to get the index. And if the hash table at the index, index is null, we're going to return null. We didn't find it. Otherwise, we need to start looking then. So we'll say my current table entry of key and value, current entry is equal to, starting here, and while the current entry does not equal null, let's keep on going. We're going to say if the key dot equals the current entry dot get key. If they match, then we're going to return the current entry. Return current entry dot get value. Right? We found the value. Great. If we didn't, then my current entry equals the current entry dot next. Get next. If we've done all that, we haven't returned yet. It wasn't existing in our table. We'll return null. Wasn't found. So we should be able to get a value back out, or null. Let's go see. So, and again, it's by key here. So let's print out here my students dot get value of, how about, let's do 124. So I should get Jane back out for 124. And let's try a number that doesn't exist. Let's try like 200. We should get null back. Oh, there it is. Okay. Now, why are you so bad at this, NetBeans? Why are you so bad at this? Yes. 2 warnings. Okay, they're just warnings, though. We don't care. We got Jane and we got null back out. So we don't actually need those warnings then, right? Can we take those back out? Compiling. Can we remove that? Can we run it? All right. Cool. If we get Jane and null, we didn't have one for 200. We did have a Jane, right, at key of 124. So we're good so far. Now remove is a little trickier. Public the remove key given a k key. So if there's a value associated, we'll return it. So again, similar idea here. So if it doesn't exist, right, we return null. Otherwise, we're going to go check for it. So before we return, right, we're going to have the value is current entry get value. Now the problem is we need to replace ourselves with what was there before. So if I have the current entry in a singly linked list, I can't I can't update the thing that comes before me because I don't have a link to it. So when we go and remove a key, we need to jump over the one that was there, right? So if I have this bucket here, if I'm going to remove this one here, I need to be pointed here to jump over it. Okay, so the case is a little bit different here. So we're going to have the current entry, and we're going to say if the current entry dot get key dot equals the key. Oh yeah, there we go. If they match. I have the wrong number of parentheses. There we go. So if the key equals the current entry key, then I'm going to have the value here, and then I can replace, because this means it's the very first one. So what I can do, I can say, hey, replace the first one with a new, replace it with the current entry dot get next. So whatever's next, it might be null, that's okay. It might be an actual entry. That's perfectly fine, not a problem at all. So if it's the first one, grab the value out, replace the first one with what comes next, and then we can return the value. If it's not the first one, right, now I need to start looking at what comes after. Because now I'm going to look at the next one and see if it matches. So I'm going to say while my current entry dot get next does not equal null, let's check if it's the next one. And so now if my current entry dot get next dot get key, if the key equals that one, so if the key matches the next key, we want to jump over, right? So then we'll get the value of the next's value, right? Because the next one matches then. Okay, so we'll get the value out. Then I need to jump my next one. So the current entry, we need a set next. That's right. So we need to come and add a set next here. So public void set next, given a table entry of s and t next, this next equals next. Okay. We want to go set the next value, set next, to the current entries get next, the next, right? Jump over it. So if it's not the first one, if it is this one right here, right? If it's this key value pair, I want to set my next to the next, which is either another key value pair or null. It's perfectly fine. If it didn't match, then let's move the next one. Current entry equals, if it does, then we return value and we're done. Otherwise, current entry equals current entry dot get next. Move to the next one. We're always looking at the one that comes after, though. That comes after. If it's not null, let's go check it. Okay, so we should be able to remove. So if we don't find it, then we'll return null. We didn't find it at all. Now we can have a nice little Boolean here like contains a k key. This one's really fun. It's the exact same logic here. We're just not returning anything. Right? Exact same thing. But we're going to return false or return true. Return false. Similar thing here. Now, you might be thinking it'd be cool if we could just check, hey, if value is not null from get value, return true. But the problem is you can have an associated value of null. Nothing says that value can't be null. So I could say 1, 2, 3 and null. Like, that's a fine, perfectly fair associated value. So you just got to be careful there. Okay? And sometimes what you do with a dictionary, you can have a like void add k key, just does an add of key and null. Right? So adding a key, or maybe that returns, I don't know. But you could do similar things, like where you add an override for, hey, let's do a null associated value. We got some options there. Okay, so we should be able to add, we should be able to remove, we should be able to get. We haven't done the iterator yet. I'm not too concerned about that. The iterators are cool, but it's just looping through, giving you one at a time. Now, what we're not going to get out of a dictionary here, we haven't really talked about that yet, is there is no ordering in a dictionary. Imperium? No, probably not. Sorry, it probably makes no sense if you jumped in the middle of a lecture. But you can always go back to the beginning. It's no big deal. Yeah, and actually a lot of it doesn't make sense unless you've actually watched all the previous lectures, because we're building on the things we've already talked about in class. But, some of it makes sense to people, and that's cool. So with a list, right, the order is maintained. With the original bag, way back the very first data structure we built, the bag had no guaranteed order. And that was fine. Right? No big deal. Oh, thanks, Professor Burp. That's right, yeah, link out to my YouTube there. We got all the previous classes and current classes. I try and keep them all out there. Or at least the most recent ones. Cool. So, with the bag, the order didn't matter, but then lists, the order did matter. We're back now to with a hash table or a dictionary that we have no guaranteed order, because I don't know, the order in which they were put in has nothing to do with what slot they go into, right? So as I'm going to iterate over, right, the idea that, hey, I'm going to give you all the keys or all the values, however you want to do it, right? I'm just going to start at the beginning and give you everything out of this bucket. Give you everything out of this bucket, everything out of this bucket, everything out of this bucket. Right? We can iterate over them. This will be quick. We can add our iterator. It's a good thing to do. Excuse me. So it's a little bit obnoxious to build the iterator. No, yeah, trying to fill out that iterator interface is kind of annoying. Probably easier if we don't. Excuse me. Yeah, maybe we'll skip the iterator. But the idea is we're just going to loop over and give you every value as you ask for them. We can iterate over it for entries. Yeah, no, it has them. So it has a hash map and a hash set in the java.util library. So you can build a Java one if you want, which is the easier way to do it, right? We only reinvent the wheel to help us kind of understand how this works behind the scenes. So we can have a hash map of type integer and string, map, a new, we got to add the import, new hash map, int string, great. And we can do the similar thing. So student map dot add. Let's add put. Sorry, it's put. Put a key and value. Sure. Remove keys. You can replace keys. Sure. Yeah, you got some cool options here. This will give you all the values. The keys will give you the set of keys. Right, so we got some cool options. But we're looking at doing it on our own, again, because the performance matters. So the last thing we want to talk about here, and then we'll wrap it up, is if I want to make a class that is hashable. What if I have a student class here? So some important notes about students, right? We're going to have a private int ID. We're going to have a private string for name, probably a private, I don't know, string for major. I don't know, all sorts of stuff that we want here. Now, some of these things are changeable and some are not. So I'm going to insert some code here. I'm going to insert a constructor. You give me an ID, a string, and a major. Great. I'm going to add some gets here because gets are great. Add some getters. Getters are great. And I'm going to add some sets here because you can change your name and you can change your major. What you can't change is your student ID. Right? You should have that exact same student ID no matter what. So this property here should be immutable, should not change. So I can even mark it, right, as final if I want. That's very helpful because it gets set once in the constructor and can't change. So then what I can do is I can add an override for get hashcode, public int get hashcode. Or what is it? Just hashcode, right? Hashcode. Right, and what we're going to do is we're going to return my id.hashcode. Or, no, integer. Oh, we just return the ID, right? Because that's our unique ID. Sure. And now it's telling me, hey, you have a hash code, you should also have equals. Because just because I can hash doesn't mean that two students with equivalent IDs, names, and majors were going to show up as equal, because the default equals method is are you the same memory address? And we don't want that. So if you're defining hash code, you should define equals. If you're defining equals, you should define hash code. So in our case, let's say, you know, which one? Should we just check ID? Or should we check name and major? Probably we only care about, I don't know, let's care about name and major too, right? Why not? Look at this. Look at that, all that generated code. How cool is that? So that added the override for equals given another object. So we can compare any object. So if we are the same, right, given the memory address check here, if my object equals their object, if our memory addresses are the same, obviously we're the same. If the other thing is null, obviously we're false. This protects us from doing null reference exceptions. And then our class is the same. If they're not the same, we're false. Okay, then let's cast that object as a student. And if our IDs are not the same, false. If our names are not the same, false. If our majors are not the same, false. If we haven't returned a false, we're going to return a true. This is redundant? Oh, that's right. Yep. Okay, so it's detecting you can just return true or false. So that's fine. We'll take the built-in code. So now I can put student objects into a hash table or a dictionary because I have the hash code. And the hash code for any equivalent student should be the same. So two objects can have the same hash code without being equal. That's okay. But two objects that are equal must have the same hash code. Because it is, if I make two different students and they hash to the same value, sure, that's okay. But if the equals method then doesn't check, right, we've got a problem. But if, you know, so hash code, you might not always have a unique ID. Maybe we're hashing name, if that's all we had. Again, that's not ideal because you can change name, but it should be a property that is immutable. So we always want to hash only immutable properties. Immutable, mutable, and oh, that's probably close. Immutable properties, because that's going to determine if I have an object and I go get it out of my dictionary and I go change some properties on it. If I call some methods that change properties and then I want to go do something with it, if that hash code changes, it's not going to be able to find it again in the dictionary. We've screwed things up. Now we have just something dangling in the dictionary. So in our case, because integer or ID is an int, I know that's what the hash code is. So if you have objects with more properties, it's like if you don't have a unique identifier for student, then that's fine. Like if you had a class like food, you might just hash the name of the food. and that's the hash code there. That's okay. Or if we got a hash code for vehicle, maybe the hash code is the make and the model, right? And the year or something, right? However you want to determine that. So your hash code doesn't just have to be a single property, but only the immutable properties. Right? So yeah, for vehicle, it might be year, make, and model. The year, make, and model should always hash because they're immutable. You can't change those things about a vehicle. You can change the color, so don't include color in the hash code. Right? If you want to include color in the equals, great. So like, hey, this 2020 Chevy Bolt that's gray does not equal this 2020 Chevy Bolt that's blue. Sure, that's okay. Or right, or maybe you want to check the VIN if you want to check that, and the VIN string then would be the property we care about, because that is not supposed to change either, and that is just a single simple property. It'll make life easy. So totally up to us, but if you want to do things, you need to do that. Now, nothing prevents us here. Now, let me show you this is a bad thing. It's a bad thing. We can just return 0. Right? Java is okay with this. We should feel terrible about ourselves because we know what's going to happen is we're just going to get a giant chain every time we're hashing these objects. Oh, very cool, Mr. Wakeler. Yeah, for Samsung S20, check for storage and color. Yeah, you could say, hey, if those two then are going to be equivalent, great. Or maybe you want to check the serial number. It depends on what you want to define for your object is what equals another object. Right, whatever we need to use there for equals. So a lot of things in life are very specific, and we can get down to a very specific serial number. Not everything is. Like my mason jar here, I would say is equal to any other quart mason jar. They should be equal. So like I'm just comparing, I don't know, the brand and the, is it wide mouth or narrow mouth sort of thing. Sorry, is there some background noise? So it determines what you want to do, but Java is fine with this. We should not do that because we'll end up with that big chain, and that's a bad thing. But you could. That's why saying that the performance of a dictionary really depends on that hash code being uniformly distributed is true. You need to make sure you're getting good hash codes for your objects so that they can be distributed across your dictionary in that hash table. That's what it depends on. Okay? All right, so let me go push this out to GitHub. We did good. It's a little after 8, so why don't we call it? We can talk more about search trees and binary trees next week. 2353. All right. And push this out here. So this is our custom dictionary. All right, any other questions, thoughts, or concerns? Again, I'm here to help. We study these things because we will better understand their performance so that we can choose the right data structure to get the performance that we need when we're solving problems. Because there's not just, as much as I love dictionaries, they're not always the answer. Sometimes you don't need to do just those. Yeah, Imperium, I've taught C++ before. I think I've got a course out there on my YouTube for it. I think I do. I should go look now. Now I'm curious. Let's see. I think I do. Hey, Professor Burp, you made it to the end. We're happy, right? So we have... Oh, that's the... Oh, a dad joke. I just got a couple fun ones, Dusty, while I grab this here. Let's make sure we're hitting all of our topics here. Let's see. While I pull up a dad joke here. Yep, so next week we'll talk about binary search trees, balanced search trees, and graphs. I think they'll be fine. The week after that is totally set aside for final project work time. And then on 8/18, we're going to plan to get together on Zoom and present our final projects. So that should be a lot of fun. And open the gallery. Open gallery. There we go. This one was good. So recently our police department put out a warning. They noticed there was some shoplifting activity happening at some of our local stores. Yeah, this old course list here. Yep. Yeah, next week will be the last lecture. But they said these shoplifters are super weird because they're grabbing clothing all of a certain size, but it's like it's progressing. So they started off, they hit one store downtown, they took all the smalls, and then they hit another store downtown, they took all the mediums. And now they're saying, hey, we need to be watchful of these shoplifters because they're still at large. On 8/11, I wasn't planning on meeting anywhere. If groups want to meet with me or individuals want to meet with me, that's perfectly fine. We can schedule that time. It's for you folks to work on it. Yep, work on what you need, and I'm happy to hop on and we can chat about things if you want to talk about it. All right, and I just found this out. Do you guys ever read the Where's Waldo books? I guess they're not really reading, but did you ever like use, I don't know, play with the Where's Waldo books? You know, I found out why he wears a striped shirt. It's because he doesn't want to be spotted. I like that one too. All right, awesome. It's been a lot of fun. Let's head out to pester someone else out in Twitch land, and we can go from there. Let me put on my ending screen here. There we go. We'll find somebody. And if not, if you don't have any other questions, so we'll meet up next week, and we can go from there. Lots of people around. Cool. Later. We're going to head over to my friend Lantern Noir, because I'm a big nerd. We'll watch him play D&D, or watch his crew play D&D. If I can get this raid to work. Splashly? Oh, sorry, I missed it. We'll have to do that next time, Imperium. Folks, take care. I'll see you around. Let me know what I can do to help. Again, I want you to be successful with this final project and have someone you can talk about. It'll be a great interview topic for you. Have fun.